So this week's lesson is on linear systems, also known as systems of linear equations, but that's really verbose and I like to use fewer words if possible. So whenever they're talking about a system in Mathland, that simply means that you're going to have two or more equations. What kind of equations are we going to be dealing with? We're going to be dealing with linear equations. And linear equations just have x to the first power and y to the first power, so there's no weird squares or things of that sort. And the graphs of those would be lines. So if we're going to have two or more equations, let's think about what this would visually look like. A linear equation is a line. So I might have a line that goes like this. Woo! Yeah! And then I might have a secondary line because we have two or more equations that might go woo! Yeah! And so if we are solving this, the point in solving it is to find the point that they share. That's called the point of intersection. And the point, since it's a point, means that it's an x and a y value will be our solution. So our solution will be a point that's an x and a y. Now, notice that points, remember, have to have parentheses around them to indicate that it is a point. Just listing two numbers with a comma in between them does not indicate that it's a point in Mathland and therefore would not be an accurate answer. So you must have the point in parentheses for your solution. Okay, that's what we're trying to find. Now, if you remember from our, we didn't do graphing yet. Our point has to hold true on both equations, the green line and the purple line. So x and y are two different values, two different variables, and in your equation you're going to have these two variables and you need to substitute it in and it'll make both equations true, the left side equal the right side. So in this particular video, I'm going to talk about just the substitution method. Linear systems is my favorite method, or my favorite concept, in part because there's so many different ways that we can actually solve these. We are only going to focus on the substitution method and the elimination method. Now, we could graph it. That is one of your possibilities, but if that point is not pretty numbers, if it's a fraction or some decimal in between there, it's going to be very hard to find out to accurately place and say, oh yes, I can clearly tell that that is 2 3/5. Yeah, that's just not going to happen. So that's why we want to know some algebraic ways of solving. So the two methods that we are going to go through is called the substitution method and the elimination method. This one, I'm just going to focus on the substitution method, and then I'll do another one for the elimination method. But what we're finding is always a point of intersection, and our solution will always be a point, an x and a y value. So here's your steps for the substitution method. We are going to solve one of the variables in one of your equations. Remember, it's a system, so I'm going to have two equations. So I'm going to solve for one variable. So in other words, I want either x equals blah, 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 everything else, or I want y equals blah, 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 everything else. That's what it means to solve for one variable, to get that by itself on one side of the equal sign. Then what's going to happen is we're going to go into the other equation. Because remember, we have two equations. We rearrange or we look for x is equal to blah, 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 or y is equal to blah, blah, blah in one of the equations. Then we go into the other equation, and wherever there's that variable, whether it be the x or the y, I'm going to pull that out and I'm going to substitute in the blah, 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 blah for it. Because remember, the equal sign, when it's x equals blah, 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 the equal sign means that those two are equivalent to each other. They mean the same thing. So I can pull one out and put the other one in. It's just like going through your English papers and replacing words with some bigger words that might make it sound better and it might take up more space. Instead of calling it a blue, I'm going to call it aquamarine. So I pull out the word blue and I replace it with aquamarine. I'm going to do the same thing here. I'm going to pull out one of my variables and replace it with that expression, the blah blah stuff. The point of that is now I'm going to have an equation that just has one variable, whereas before we had two variables, an x and a y, and you can't solve and get a value for x when you also have a variable y, and vice versa. So we needed to get rid of one of our variables, and so this is how we substituted in an expression that has just the one variable, and now we can solve that variable. Now that's just going to give us one of our solutions, and that's the best thing about linear systems. It's like, oh, yay, I solved this. Oh, I'm not done yet. I get to continue on, because that is only one coordinate of our point, and our point has an x and a y. So once we know what one of the variables is, we do what's called back substituting, and we replace that value back into a previous equation to solve for the other unknown or the other variable. And another wonderful thing about linear systems is that you can check your answer to make sure that it's right. It has to be a point that's on both of our lines, so it has to hold true for both equations. So we can check and make sure that we have the correct answer. No reason to get them wrong. So let's go through a couple. Here's my system. My first equation is y equals 5x minus 7. My second equation is negative 3x minus 2y is equal to negative 12. So in this case, we are very fortunate because in the first equation, I already have y solved for. It's y is equal to this 5x minus 7. So I already have that first step done. So now I know that y is the same thing as 5x minus 7. Wherever there is a y, I can replace it with 5x minus 7. So now I go into the equation that I haven't looked at yet, which is the second one, and I say, aha, here is a y. That is the y that I'm going to pull out and replace with 5x minus 7. However, I need to look at the y and make sure that I have the same operations happening. Right now, it's negative 2 times y. So when I pull the y out and replace it with 5x minus 7, I need to preserve that operation that negative 2 is being multiplied by that entire quantity. So when I rewrite it, it's going to be negative 3x minus 2 times the whole quantity of 5x minus 7. I must use my parentheses to make sure that I use my distributive property. Everything that is equivalent to y has to be multiplied by that negative 2. Now you can see that I have an equation that has the variable x only in it, whereas before I had x and y. And as I stated before, we can't find a value for x if I don't also have a value for y. And we can't just replace random numbers. We need to make sure that it's the correct values. So now I can solve this. Get rid of my parentheses first, as we've learned last week. So remember, this is a negative 2 that's being multiplied inside. So I have negative 3x, then it's a negative 2 times 5x, which would be a negative or minus 10x. Negative 2 times a negative 7 is a positive 14, and that's equal to my negative 12. The next step is to do what's called the cleanup method, okay, is to combine like terms on either side of the equal sign. After we've used our distributive property, oftentimes we have like terms and we want to simplify them. So here are my like terms. They both have an x. Now these are on the same side of the equal sign, so I'm just combining them. I don't have to switch signs because I'm not going from one side of the equal sign to the other. I just have two piles over here and I want to make it into one pile. And so that's going to make it a negative 13x plus the 14 is equal to a negative 12. Now my next step is to get the variable term on one side of the equal sign and any any constant terms on the other side. Now the negative 13x is my only term that has the variable, so I don't have to do anything else there. I just need to move the 14 to the other side. It's a positive 14, so I have to do the opposite operation because I'm taking it off of one side and I have to do the same thing to the other side to keep it balanced. Remember, think about your scales of justice, right? If you have scales here, if I take something off of one side to keep it balanced, I have to do the same thing to the other side. So that's going to give me a negative 13x is equal to, and you can check that that'll cancel out, 14 minus 14, whoopsh, negative 12 and a negative 14. Those are both negatives that we are adding, so you add them and keep the sign. Now finally, to get x by itself, we divide to conquer. I need to get rid of the negative 13, so I have to divide by the negative 13. Division is the inverse operation of multiplication. That's why the sign goes with. With addition, the inverse operation is subtraction. That's why you switch the sign, is because it's a different operation. Okay? So we divide on both sides. Negative 13 divided by negative 13 is a positive 1x. Negative 26 divided by negative 13 is a positive 2. Now remember, we're not done yet, because that was only one part of our solution. Our solution has to be a point, an x and a y value. So now I'm going to do that other step, that next step, which says back substitute. This is the step that's actually easier in the substitution method than it is in the elimination method. And the reason for that is because in that equation that we had set up, that we had one variable all by itself right up here, I can easily plug that x equals 2 in for that x, and I just have to simplify the right side. I don't really have to do any solving. So I would have y is equal to 5 times that x value of 2, and then minus 7. So again, I just replaced the x with its value that I solved for down here. And now I can simplify. Order of operations says I do multiplication first, and then I would do the subtraction. So I get y is equal to 3 when x is equal to 2. That would be my solution. Now take the extra moment to check. Remember, to check, the point has to hold true for both equations. Now, because we solved for y using that first equation, if I plug 2 in for x and 3 in for y, I better get the left side to equal the right side, because that's how I just solved for y, was using that equation up here. So really, when I check, I just have to check in that other equation. And I don't have to do a big check here. It's negative 3 times my x value of 2 minus 2 times my y value of 3, and that's supposed to equal negative 12. Oopsie. Don't lose your signs. Negative 12. There, let me write that neater. All right, so now simplifying, we have negative 6 minus 6 is equal to a negative 12. Well, remember, subtraction is the same thing as adding the opposite. So a negative 6 plus a negative 6, if you're adding two at the same signs, you add and keep the sign. So that's going to give me a negative 12 equal to a negative 12. The left side equals the right side, so it checks. So now I can write my solution. And remember, your solution has to be a pair, and it's always alphabetical. X value first, then the y value. And that was solving using your substitution method. Let's try another in which the variable isn't already solved for. So in this system, I have negative 4x plus 9y is equal to 9, and x minus 3y is equal to negative 6. You'll notice that in neither of the equations do I have either x equals something or y equals something. So we're going to have to rearrange the equations to solve for either x or y. It's going to be easier to solve for x in the second equation because the coefficient, or the number in front of x, is a 1. That's the god of Mathland. We don't see him or it, but it is always with us, whether we see him, her, it, or not. Okay? So if there's an x all by itself, it's really just a 1x. And that's going to be what you're looking for always in the substitution method, because that's going to be the easiest to rearrange the equation. Okay? To rearrange that equation, all I need to do is get rid of the minus 3y. So to get rid of a whole term, it's being subtracted, so I have to do its inverse operation. So I have to add the 3y. And again, whatever I do to one side, I have to do the exact same thing to the other side. Now, simplifying that, I get x is equal to, that cancels out. Now, negative 6 plus 3y, those are not like terms because the 3y has a y and the negative 6 does not. So we're going to make a binomial here, or two little terms. I like to put my variable term first, especially in this case because my variable term, the term that has the variable, the 3y, is positive, and the constant term, the negative 6, is negative. If I end up writing it with the negative 6 first, chances are I'm going to forget the negative in a future step. So I'm going to write it with my positive term 3y first, and then subtract the 6. I could have written it as negative 6 plus 3y, but make sure that the negative is still in front of the 6. This is not the same thing as 6 minus 3y. Now you've changed the signs on both of them, and that's illegal in Mathland. So now I have x is equal to this 3y minus 6. So now I go into the equation I have not manipulated, which would be the first equation, and I look for that I look for that x that I'm solved for here. Here's my x, and now I get to replace that with 3y minus 6 because those are equivalent to each other. Do that over here. So I've got negative 4, and then it's going to be times that 3y minus 6. And then finish the rest of the equation. It's still plus 9y equals 9. Now, once again, we have to get rid of those parentheses, so I have to use my distributive property. So this is now negative 12y. Negative 4 times a negative 6, so it's going to make that a positive 24. Plus the 9y equals 9. Now we combine like terms, because once again, these are not on opposite sides of the equal sign, but I'm just simplifying this expression. Negative 12y plus 9y is going to be negative 3y plus 24 equals 9. That's me getting an email. Okay, now we get the variable term on one side and everything else on the other side. So I need to move that 24 by subtracting it. Because it's a positive, I need to do the opposite, which is a negative. Okay. So now we simplify, and I have this negative 3y is equal to, now 9 minus 24. 24 is the bigger number, so I would go 24 minus 9, which is 15, but I started with 24, and that's negative, so my result is a negative 15. And then finally, we divide to conquer. Negative divided by a negative, multiplying or dividing, two of matching things, that's a good thing. So that's going to give me a positive 5. Again, I'm not done yet. I just found out what y is equal to. Now I can go back into this equation where I've x already solved for, and I can replace the y with 5 and solve for x. So again, it's that same equation of x is equal to 3y minus 6, but I'm taking the y out and I'm replacing it with the value that we just solved for. Now I can simplify. Now that I've found my solution seems to be x is 9 and y is 5, I'm going to check. Now, I found out x is 9 when y is 5 from this equation here, which is a variation of the second equation here. Okay, so those equations are equivalent to each other right there. It's just that they look different because we rearranged the order of it. So I don't have to check in that second equation because it should work because that's how I just solved for 9, or for my x value to be 9. I just now have to go into the other equation, which is that top equation, and simplify from there. So I write it all out, and I have my equation there, and I replace the x with 9, and I replace the y with 5, and now I simplify. Negative 4 times 9 is a negative 36. 9 times 5 is 45. 45 minus 36 is indeed 9. Those are 9 away from each other, so it checks. So now I can write my solution, x value first, comma, y value second, in parentheses. So that is our substitution method. Remember, we solve one variable in one of the equations, so we either have x equals blah blah or y equals blah blah, and we go into the other equation and we replace either the x or the y with that blah blah, and we solve. Then you go back to find your other variable, because remember, you're going to have two solutions, an x and a y, and then always check. No reason to get these wrong, because you can always check to make sure that you have it right. And be careful of your negatives.